This should be a quick lesson. You need your calculator out. We're going to examine some of the things that are useful on your calculator if certain questions come up on the Regents exam. So the title of 16.5 is the area under a normal curve and normal approximation to binomial distribution. So you see on the right here we have back to our normal distribution curve. Here it is. And we can tie this into probability because each of these little sections, like the 19.1%, could be considered a probability. 19.1% probability of falling half a standard deviation from the mean, because that would be a half a standard deviation lower than the mean. If I looked at the probability of falling within a standard deviation of the mean, then of course we'd be adding up these four percentages, and we know already that that's 68.2% probability, which is 0.682. So the calculator has a way, let me just do this for a second. There we go. There we go. So the sections under the curve can be interpreted as the probability that a score occurs within that region. We can also use our graphing calculator to find the percentage or the probability of a certain range of scores. So that means, that really opens it up, because that means we don't just have to use the mean and one standard deviation or two standard deviations or three, like we always set up our curves, or even the halvesies. We can go from any score to any other score. So let's take a look at the steps and then try a couple on our calculator. The steps are to hit your second vars key, and above the vars you can see it says DISTR, and that's short for distribution. And we're going to choose number 2, which is the normal curve, and that's cumulative distribution frequency, I think, for the CDF. So normal CDF. When we choose that, you'll get something that looks like this on your calculator screen, okay? And it's going to need 4 values. It's going to need the low score or value that you're looking at, the high score, the mean for that data, and the standard deviation for that data. So you're still going to need to go through and do the 1 var stats and get these things. Get the mean and the standard deviation. And then you can still set up your normal curve with your values. But we're going to be able to put this right into our calculator. So our first example says the height of a certain plant is normally distributed. You want to look for those words. With a mean of 20. Excellent. So we know the mean already. And a standard deviation of 3.2. So we know when we do this, we're going to put a 20 and a 3.2 in there. So given that this is the mean and the standard deviation for these plants, now I could go and find the probability that a selected plant falls within any range. So I'm looking for plants to be between 23.2 inches and 26.4 inches. So let's go into the calculator. And let me just clear out my window. We're going to hit second vars. All right. And we want choice 2 right there, normal CDF. All right, there it is in our home screen. Now we want that lower value, 23.2, comma, and the upper value, 26.4, comma, 20, comma, comma's not behaving up here, and 3.2 for the standard deviation. Now, if you have the newer operating system, you put these in one at a time, going down, and then you use the paste function, and it'll paste that into your calculator. So this says that the probability that we get plants between these inches here is going to be 0.135905197.5, which is, let's see, we'll say that's approximately 13.6%. Okay, so there's our probability. Those aren't bad, those are pretty easy. So, let me just go back to that real quickly. Again, the beauty is that if we were to set up our graph and we knew the mean was 20 and the standard deviation was 3.2, we'd know that this is 23.2, we'd know that this is 26.4, and then subtracting, of course, we could go to the left, 16.8, etc. Subtract another 3.2, 13.6. If we're looking for the percentage between these, now we can put anything in there, any number I want. But notice what we got was right between the 1 and the 2 standard deviations. Put that in so that you could see that it works. And that percentage there is indeed 13.6%. But any values could go in there. I don't need to have a perfect z-score. All right. Now to something we did yesterday, Bernoulli trials. We can actually use our calculator as well for Bernoulli trials. And here is the formula that we used yesterday. N choose R, P to the R, Q to the N minus R, where right away we go and figure out N, R, P, and Q. So this becomes useful when they're asking you for example, we'll go do a couple, 100 flips and I need at least 60 to be heads or tails. Well, at least 60 means we'd have to do 60, 61, 62, 63, all the way up to 100. We talked about yesterday, nobody wants to do, 8 of these or 7 of these. Can you imagine having to do all of those parts for 60 through 100? So this is a small example. When 6 coins are flipped, the number of tails showing could be 0 tails, 1, 2, 3, 4, 5, or 6, all tails. The table below shows the probability that we get exactly no tails. So this was done using a Bernoulli probability. All right, this particular one, let me get a smaller, would have been 6 choose 0, 1/2 to the 6th and 1/2 to the 0, and that's what you would get. This one was computed using 6 choose 1. I did that backwards. Sorry about that. 1/2 to the 0, 1/2 to the 6th. This would be 1/2 to the 1, 1/2 to the 5th, and this would have been 6 choose 2 to be tails, 1/2 squared, 1/2 to the 4th, etc. So these are all the probabilities for getting exactly this many tails. You could try one of those if you're curious. But what if we want, you know what, turn to your examples. I thought you had one. Yep, you do have one. On your examples, it says the normal curve would be useful if you have to find the probability of getting at least 60 heads in 100 tosses. So I want you to look at that one. It's on the third page of this lesson. So we'll go right to how you can use this. So here, N would be 100. We're going to toss a coin 100 times. R would be 60 or 61 or 62 or all the way up to 100. The probability of getting the heads is a half, and the probability of not the heads is also a half. So this would be a lot for the Bernoullis, a lot of work. But we can use normal CDF in a real interesting way. So we're going to use our calculator. Now we still need the low value and the high value and the mean and the standard deviation. Okay. But now it's a little trickier, The low now is going to be your R value, your low R value, minus 0.5. Your high is going to be the number of rolls plus 0.5. I'll explain that in a little bit. Your mean is now figured out by multiplying n times p, and your standard deviation is figured out by doing the square root of npq. All right, now all of that is one page back here. So to calculate, this really should be at the top, to calculate the probability that an event occurs at least r times in n trials, we would add up all the probabilities from r to n using this. And here's what I did. Exactly what I wrote. The r value minus 0.5, because we have to go a little bit to the left so we know that the portion is included. And n plus 0.5, for the same reason, we go a little farther to the right of n, a little farther to the left of r. The mean is calculated by multiplying n times p, and the standard deviation square root of np and q. So let's go back and do this one. Our r value, we just have to use the 60, and we just have to use the n. So this would be r minus 0.5. That looks like a funny thing. So that would be 60 minus 0.5, 59.5. The high is 100 plus 0.5. N times p, here's p right here. N times p is going to be our mean. So that is 100 times a half, which is 50. And the square root of NPQ is the standard deviation. So we need NPQ square rooted. And I usually just put them, I write them out first. So I would have 100 times a half times a half. Just to see first, is this easy to do? And 100 times a half is 50, and times a half again is 25. So the square root of 25 is 5. So that's a beautiful number. I can just put that in. So let's go to normal CDF and give this a try. Second distribution, or second vars. Normal CDF is choice 2. And here we go. 59.5 is our low, because we're doing at least. 100.5 is our high, comma. Our mean was n times p, comma. And our standard deviation was pretty, just a 5. All right. And so the probability that that would occur is 0.029, or 0.287164928. Percentage-wise, boom, boom, 2.9% probability, very low, that you would get at least 60 heads in 100 tosses. Okay, So these are the two uses for normal CDF. They have had a question like this on a Regents, but it's not very common. Let's go back and look here where the notes are. And I'll just do a little bit more so we can do binomial expansion also. The probability that a team will win a game is 3/5. So that means they'll lose 2/5 of the time. Use the normal approximation to estimate the probability that the team will win at least 10 of its next 25 games. So 25 games, at least 10 would be 10, 11, 12, all the way up to 25. Again, too much work. Okay, see if you can fill these in now. Since it's a low, we're low. It's R minus 0.5. N would be the upper limit. It would be way up here. So we want this whole range, but a little bit lower and a little bit higher. So we add on 0.5 to make sure we've included all the intervals. The mean, you have to remember with these is N times P. Get all these erasures out of here. N times P. So 25 times 3/5. That's not bad. That would be 15. And the standard deviation is the square root of NPQ. So 25 times 3/5 times 2/5. Look at that, these two 5s will cancel with the 25. So square root of 6. That's exactly what I'm going to put in to the calculator. Okay? So, back to the calculator. Let's give this a shot. Second distribution, normal CDF, choice 2. And the low was 9.5. The high was 25.5. The mean was 15. Don't forget your commas. And the standard deviation was that crazy square root of 6. Pop it out of there. And close it up and hit enter. So the probability that that would happen, very high, 0.987. Should do 0.987618266, which is 98.8%. So that's a very high percentage of occurring. All right, we did 2 at least questions. What if the question said at most? So here's one with at most. Again, these are really Bernoulli, but they're so large of an R value that we wouldn't do it by hand. So we have a family with 7 children selected at random. What is the probability that the family has at most 4 boys? 7 children, at most 4. So 4, 3, 2, 1, and 0. And that's not too much work, but we're going to use this anyway. Probability that we pick a boy is a half. Probability we pick a girl is a half. So let's talk about our normal CDF this time. Because if we're doing at most, then we're looking at a value down to 0. 0 would be the low. So this normal CDF, we start with 0 as the low. And you see it there. There's 0. So we're going to sort of flip this around. We're still going to add 0.5 to this one, so 4.5. The mean is still N times P, so 7 times a half. I'm just going to go with 7 halves there, or 3.5. And the standard deviation is still square root of NPQ. NPQ, square root of NPQ is square root of 7 times a half times a half. I'm just going to go with square root of 7/4, and that's literally what I'm going to put in. So let's do this, and then we're done. We'll find the probability that we have at most 4 boys. So, second of ours, and our choice is 2, and our low is 0, comma, our high was 4.5, comma, we had 3.5 for our mean, and the square root of 7 divided by 4. Let's pop out of that square root, pop out of the normal CDF, and we've got our probability, about 77%. I'll do abouts here. All right, that's it. You never know if you're going to get one of these, but it's kind of handy to do. We can do Bernoulli's with this normal CDF. You have to use it if you get a big, huge number for your at least or at most. And then you just have to think of your low and your high. Add on 0.5, subtract off 0.5 unless it's 0. Your mean is n times p, and your standard deviation is a square root of NPQ. Could come in handy.